All right, here we are for a practice problem on dimensional analysis. As a reminder, dimensional analysis is useful for a few different reasons. Among those, it can allow you to figure out an equation that you have forgotten by taking the units of the givens and mixing those things together to get the units you want out. The other thing it's useful for is checking that you have got a correct answer at the end. This is technically the third thing you can do with it, and it's probably the least interesting of them. If you forget the units of a constant, you can work it out based on the units that surround it. Alright, so here we go. Newton's law of universal gravitation is represented by the formula force is equal to constant big G times mass 1, or big M in this case, times mass 2, or little m in this case, divided by r squared, where r is the distance between the objects. In this formula, F is the magnitude of the gravitational force exerted on small objects on each other. The wording here is a little awkward. Let me see. Where F is the magnitude of the gravitational force exerted by... Let me fix this while we're here. Exerted by a small object on another object. My apologies. I thought I'd have caught all of my weird little awkward mistakes by now, but apparently I'm still finding them from time to time. Yep, I did catch one other thing I want to fix while I'm here, so let me change it, and then we'll go back through this. Alright. Ooh, the squared is missing there too. Alright. So Newton's law of universal gravitation is represented by F is equal to big G times big M times little m divided by r squared, where F is the magnitude of the gravitational force exerted by a small object on another object. Big M and little m are the masses of the object, and r is the distance between those objects. Force has the SI unit, kilogram meter per second squared. What are the SI units of the constant big G? All right, so for this, big G, we don't know its units. We will leave it as big G. Everything else, we're going to replace the letter with its units. So F becomes kilogram times meter per second squared. That is going to be equal to big G, which we don't know its units, times kilograms for big M times kilograms again for small m, all over r squared. Well, r is measured in meters, and that's squared, so on the bottom we have meters squared. Summarizing, we have kilogram meter per second squared is equal to big G kilograms squared over meters squared. All right. We just need to isolate big G and we'll find its units. So as you can see, we'll multiply by meter squared divided by kilogram squared on both sides. And that will move our stuff over. All right, so we get kilogram meter cubed over kilogram squared second squared. I should have caught that. Cancel that kilogram out. And we get meter cubed over kilogram second squared. Okay, so in base units, it's meter cubed over kilogram second squared for the constant big G in gravitation. We will actually get to this around chapter 12 or 13, depending on which class you're in. So we will be seeing this constant show up eventually, and we'll be using it. It'll be fun, sort of. All right. That's actually it for this one. Again, it's a good habit to practice. Always check your dimensions. When you finish a problem in variable form and you put in all of your numbers, make sure you also put in their units. Make sure you cancel their units. Make sure you get the units you expect. Because if you don't get the units you expect, there's a mistake somewhere. And it can save your bacon on a test, which is always nice. All right. That's going to be it for this practice problem. I'll see you in the next practice problem or video. Oops.